Welcome to the deep dive, where we take your stack of source material and really just pull out the essential, fascinating nuggets of knowledge you need to be well informed.
And today we are diving into a true unsung hero, a material that, quietly protects your food, it delivers your water.
And it might even one day shield an astronaut from radiation. We are talking about high-density polyethylene.
Or HDPE.
Yeah.
You probably know it as plastic code number 2. You see that little triangle on your milk jug or maybe a shampoo bottle.
Right. And the big question is, why are we dedicating a whole deep dive to, a humble milk jug?
Well, the answer is it's shocking resilience. It's an incredible material.
Absolutely. This one material is, it's arguably one of the most important components in modern infrastructure in rigid packaging, and the science behind it is genuinely mind-blowing.
So our mission today is to unpack a stack of sources. We've got a comprehensive literature review, a detailed comparison paper.
And we're going to use them to understand precisely what makes this material so incredibly durable and, I think crucially, where it's going next.
Right. HDPE is one of the most widely produced thermoplastic polymers in the world. It's prized for this exceptional combination of strength and lightness, chemical resistance. It's just so versatile.
So we're moving from the molecule's tidy little structure, all the way up to discovering why this plastic can literally survive underground for centuries.
And we'll get into some exciting new technologies like 3D printed workboats and even aerospace radiation shields.
Yeah, for anyone listening who thinks plastic is just, well, plastic, prepare to be surprised.
Yeah.
Okay, let's unpack this.
Let's do it.
So let's start at the foundational level, the molecular structure. When you hold a flimsy plastic bag, that's low-density polyethylene, LDPE, but when you hold a tough, rigid container, that's HDPE.
And the difference feels massive.
It's huge.
Yeah.
How can two things made from the same basic chemistry be so different?
It all comes down to architecture. Think of the base ethylene molecule as a building block. In LDPE, when these blocks link up, they branch out in these disorganized, messy patterns.
Like a giant pile of tangled headphone cords.
That's a great analogy. They just can't pack closely together.
And HDPE, I take it, cleans up that mess.
Precisely. HDPE has this fundamentally linear molecular architecture. Very, very minimal branching.
So like perfectly straight lines?
Almost. We often analogize the molecules to tightly packed soldiers standing in perfect formation. Because they are so straight and aligned, they can stack incredibly tightly.
So it's all about molecular efficiency.
That's exactly right. And this tight linear packing, it forces the material into a state of high crystallinity. We're talking typically 60 to 70%.
And that crystalline structure, that's the source of its strength.
That's the physical source of its rigidity, its chemical inertness, and its amazing strength-to-weight ratio.
Okay, so let's put some numbers on that, because that neatness, it translates directly into a massive performance difference.
It really does. The data we reviewed highlights this so clearly. Mechanically, HDPE has a tensile strength. That's the resistance to being pulled apart, of about 38 megapascals, or MPa.
38. And what about LDPC?
Contrast that with LDPE, which registers only about 21 MPa.
Wait, hold on. That's a 17 MPa difference. That's nearly an 80% increase in tensile strength.
It is.
So does that mean it can just support heavier loads or resist puncture better? What's the real-world impact?
It means both, but the rigidity is the key. It moves HDPE from being, just flexible packaging to being structural. You can build a heavy-duty storage shelf out of it. You can build a huge drainage pipe.
Things you could absolutely not do with the 21 MPa LDPE.
No way. And the density stays about the same, which means you get this massive boost in strength without it getting substantially heavier.
That is a huge leap in performance just from controlling the molecule's shape. So how do they do that? You mentioned low-pressure polymerization.
Right, you need really fine chemical control. The architect behind that control is the catalyst system.
A catalyst.
Specifically what are known as Ziegler-Natta catalysts. They're often titanium-based compounds, like titanium tetrachloride.
Ziegler-Natta, that sounds advanced. What is that catalyst actually doing, in simple terms?
Think of it like a microscopic assembly line. It provides this precise surface that forces every single ethylene molecule to connect end to end. It prevents those messy branches from ever forming.
Ah, so it's a template.
Exactly.
Yeah.
Without that specific catalytic control, you just end up with the flimsy branched LDPE. This precision is what makes sure those molecular chains line up like those perfectly organized soldiers we mentioned.
Okay, so we have this incredibly strong, tidy molecular structure. Let's talk about where that durability meets the ultimate real-world test, the environment.
Infrastructure.
Yes, because if a material is going to last for decades, it has to handle immense pressure and, hostile environments, usually underground.
So pipes.
Piping is the absolute prime application for HDPE. These things are engineered to handle pressures often exceeding 500 psi.
Wow.
They're critical for everything: municipal water, wastewater, natural gas. They are built to last because they have to resist corrosion, chemicals, and cracking.
And when you say built to last, how long are we talking?
Mm.
50 years? More. The durability is the showstopper here. The source material we looked at gives concrete data. HDPE pipes have projected operational lifespans of 50 to over 100 years.
100 years.
Over 100 years. Compare that to traditional rigid materials like PVC, which often tap out around 25 to 50 years.
That's incredible. A century of service for a plastic pipe. But, let's be honest, replacing municipal piping is incredibly expensive and disruptive.
And that 100-year lifespan is the economic justification. The long-term cost of failure is the driving factor. Traditional materials corrode, roots get in, they get brittle.
And you have to dig up the whole street.
Constantly.
Yeah.
HDPE is chemically inert, it's flexible, and it doesn't corrode. You bury it, and you essentially forget about it for a lifetime.
And speaking of resistance, there was a fascinating finding about its ability to handle internal shocks.
Yes. This is where it really separates itself from rigid pipes. HDPE has a staggering 2,500 times greater resistance to a phenomenon called water hammer.
Water hammer, that sounds violent. What is that?
It's the shock wave created when water moving rapidly through a pipe is suddenly forced to stop, like when a valve slams shut.
Oh, right.
In a rigid, brittle pipe, that pressure surge can cause an immediate crack or failure. But HDPE is flexible enough to absorb that shock. It's like an incredible internal shock absorber.
So it's the quiet workhorse, keeping our infrastructure stable for 100 years. Okay, let's move above ground. Packaging. The milk jug.
Right. HDPE dominates rigid packaging because of its barrier properties. It has near zero water absorption, less than 0.01%.
Which means it keeps things fresh.
Exactly. It keeps moisture and oxygen out, extending shelf life. Plus, it's incredibly safe for us.
Which is why it's the preferred container for food and drinks.
Absolutely. Its food safety credentials are rock solid, established globally through certifications like the FDA's. It's chemically stable, so it doesn't leach anything harmful into your food.
Now for the biggest surprise. An application that requires not just strength, but absolute biological neutrality and near-perfect friction reduction. Medicine.
This is maybe the most incredible transformation of the material. There's a special variant, ultra-high molecular weight polyethylene, UHMWPE.
A mouthful.
It is, but it's an FDA-approved, gold standard biomaterial. The data shows over 700 medical devices currently approved for clinical use rely on this one polymer.
700. That's a huge footprint in medicine. How does a plastic become a gold standard for something as critical as a joint replacement?
The key is that ultra-high molecular weight. The chains are just exponentially longer and more entangled than in a milk jug. This makes it incredibly dense and smooth.
And where is it used?
Its primary use is in joint replacements, specifically the articulating surfaces in hip and knee implants. It's used because it has a remarkably low friction coefficient and exceptional wear resistance.
So instead of metal grinding on metal or on bone, it's plastic gliding on metal.
Exactly. That low friction is life-changing for patients. The biological inertness means the body doesn't reject it, and the joints can last for decades, restoring mobility. It's a proven life-extending technology.
Amazing. Protecting our food, delivering our water, and replacing our joints. Okay, let's pivot to what many people think of first when they hear plastic sustainability. Why is HDPE considered a hero of the circular economy?
It comes down to its high recyclability. It's labeled with the #2 resin code for a reason. Recycling it is both environmentally and economically sound.
How so?
Environmentally, the process achieves a 50% energy saving. And it reduces greenhouse gas emissions by more than 30% compared to making virgin polymer.
And this is where that molecular stability really pays off, right? Many plastics degrade when you recycle them.
They do. But HDPE demonstrates remarkable recycling stability. It maintains its essential mechanical properties through up to 10 consecutive recycle cycles.
10 times? That's almost unheard of for a commodity polymer.
It is. Imagine baking a cake 10 times and it's still coming out perfectly structured every single time. That's the kind of stability we're talking about.
Which has to create a huge economic incentive.
Absolutely. The source we looked at notes that recycled HDPE, or RHDPE, costs about $2.50 per kilogram. Virgin material is around $8.50 per kilogram.
That's a 70% cost saving.
It's massive. It makes it highly desirable for manufacturers trying to meet sustainability goals and, just reduce their production costs.
So it's strong, safe, reusable, and cheap to recycle. But every hero has an Achilles heel. What are its limitations?
We have to acknowledge three main weaknesses. First, heat. HDPE has a restricted maximum continuous service temperature of about 80 degrees Celsius. It starts this often pretty low, between 110 and 125 Celsius.
So no hot fill packaging, you can't put boiling water in it.
Precisely. The material loses about half of its tensile strength near that melting point. So it's inferior to something like polypropylene, which handles heat much better.
Okay, what's number two?
UV sensitivity. Unmodified HDPE degrades under prolonged sun exposure. The molecular chains just break down.
So for outdoor applications.
You need UV stabilizers. Think of it like a chemical sunscreen for the plastic. But even with those additives, you're typically only looking at about 5 to 10 years of weathering resistance before it deteriorates.
And the third limitation, something engineers have to worry about, is creep.
Yes, creep. It's a time-dependent deformation under a sustained load. So imagine putting a heavy object on an HDPE shelf. Over years, that shelf might slowly, permanently sag.
Right.
So engineers have to use pretty significant safety factors in their designs, which can limit its use where you need absolute perfect dimensional stability over a very long time.
But this is where it gets really interesting. Scientists know these limits, and the research shows they're transforming this commodity plastic into something high performance.
They are. The literature review we read details some credible innovation, especially with hybrid nanocomposites. For the aerospace sector, for example, they're developing systems that combine carbon nanotubes and graphene oxide within the HDPE structure.
So they're taking the basic plastic of a milk jug and adding super materials. Why?
To enhance gamma ray attenuation. In essence, they're creating radiation shielding for deep space missions.
Wow. From protecting milk on Earth to protecting humans from cosmic radiation. That's a staggering leap.
It really is. And they're also working on its mechanical weaknesses. Research shows that reinforcing the matrix with a ceramic powder like silicon nitride can improve tensile strength and stiffness by about 20%.
Just making it tougher.
Much stiffer and harder to break.
And what about 3D printing? Can we actually print large, durable structures like boats with this stuff?
The field is advancing so rapidly, there are large format additive manufacturing initiatives that are proving it's feasible for maritime applications.
So 3D printed boats.
They've done it. Collaborative projects have successfully developed 3D printed HDPE workboats. Its flexibility and impact resistance are actually ideal for marine environments.
And finally, what about the big one? Plastic pollution. How are scientists making this super durable material? Well, less durable when we want it to be.
This is critical work. Scientists are working on smart polymer blends. For example, combining HDPE with thermoplastic starch. The goal is to introduce what they call tunable biodegradability.
Meaning it only degrades under specific conditions?
Exactly, like in an industrial compost facility, but without compromising its durability during its actual service life. It's an ingenious approach to the pollution problem.
Okay, to summarize what we've discovered today, let's leave you with 3 key takeaways about this invisible hero, HDPE.
First, molecular efficiency is everything. That simple linear structure, the high crystallinity, that's the source of its superior strength and chemical resistance, which enables it to last for decades underground.
Second, it's a circular economy champion. HDPE is highly stable and remarkably recyclable. It can go through up to 10 processing cycles, which offers huge economic and environmental benefits.
And third, it's a material platform for the future. Recent innovations are transforming it from a simple commodity plastic into a high-performance material for really specialized fields.
From low-friction medical implants that restore mobility to, nanocomposite aerospace shields that protect against gamma radiation.
Exactly. And if we connect this to the bigger picture, HDPE just exemplifies how modifying the structure of a common material, even slightly, can unlock this profoundly diverse range of functions.
Which raises an important question for all of us. Given its excellent durability, its proven long life, and its established high-yield recyclability.
Right. Should we focus less on entirely replacing established polymers like this and more on accelerating the development of the high-tech additives and advanced manufacturing techniques like 3D printing that make it even more sustainable and capable?
Something for you to mull over next time you reach for that milk jug. Thank you for tuning in to this deep dive.
We encourage you to subscribe for more insights and surprising facts about the world around you.